Hi everyone, my name is Chen, and Dr. Jaewoo is my PhD advisor. We are coming from the University of Georgia. Nice to meet you in my presentation, and hope everyone is staying safe and healthy. The title of our paper is Renyi Differentially Private ADMM for non-smooth regularized optimization. I will start with some background and motivation of our research. Since the widespread usage of machine learning, concerns on privacy of individuals in the training data have led to extensive research on protecting sensitive information of humans, which is especially true in medical records, financial records, or academic records. Differential privacy has now become a rigorous and state-of-the-art standard for privacy-preserving machine learning because of its mathematical guarantee that the model output is not significantly influenced by the presence or absence of one and each observation, so that it protects against strong adversaries regardless of side information. It also quantifies the privacy leak through privacy parameters, so that it allows for privacy utility trade-offs. Many machine learning tasks can be formulated as empirical risk minimizations. In addition, people usually apply regularizations on training ERM models to prevent overfitting, especially when the training data are small to medium-sized, which is also the domain with higher privacy risks. Non-smooth regularizations are also applied for feature selection, aiming for a sparse model. However, due to the nature of non-differentiability of non-smooth regularizations, it usually needs some extra effort to train the model compared to smooth regularizations. Let me highlight the main contributions of our paper. First, we propose two efficient algorithms for solving non-smooth convex optimization problems, satisfying a recent privacy framework, Renyi Differential Privacy. In our proposed algorithms, each subproblem is solved exactly in closed form. Second, we apply the privacy amplification result for RDP to stochastic ADMM and show that the inherent randomness in subsampling process can be used to achieve stronger privacy protection. Then, we empirically show that the effectiveness of the proposed algorithms by performing extensive empirical evaluations on generalized linear models, comparing with other baseline algorithms. And the results show that in high privacy regimes, our algorithms outperform baseline algorithms in terms of classification or feature selection. Differential privacy is formally defined here. Intuitively, privacy is guaranteed by limiting the impact of every individual element of the dataset to the output of the machine learning model. The parameter epsilon is the privacy budget, meaning how large privacy we want to pay off for the training. If delta is 0, it is pure DP. Otherwise, it is approximate DP, where delta must be chosen as cryptographically small. There are also several extensions to the traditional differential privacy. A recent one is the Renyi Differential Privacy, or RDP, which stands between pure and approximate DP. In RDP, the privacy is achieved by bounding the Reny alpha divergence between the output distributions of the mechanism applied on neighboring datasets D and D prime. A mechanism satisfies alpha epsilon RDP if the divergence of order alpha is bounded by epsilon. We say RDP provides stronger protection than approximate DP due to it can be converted to approximate DP for any arbitrary small delta, as given by the proposition. In practice, one method to achieve RDP is the Gaussian mechanism, which injects noise sampled from a Gaussian distribution scaled to the L2 sensitivity of a vector-valued query. Therefore, there can be a correspondence between the scale of noise, sigma square, the privacy level, epsilon, once the sensitivity is fixed. Many machine learning problems can be formulated as regularized optimization problems of this form, where L is the loss function on one individual. To avoid overfitting, we usually apply a data-independent regularization term into the loss function. For some applications, the regularizer h of x can be a non-smooth function such as a L1 norm or nuclear norm. In this paper, we propose two optimizations algorithms that satisfy Renyi differential privacy, and we make the following assumptions on the loss function. Convexity means that both the data-dependent function f and the regularization term h are convex. Differentiability means that the non-regularized data-dependent function f is continuously differentiable with respect to the model x. Bounded gradient means that there exists a constant c by which the norm of the gradient is upper bounded for all models in theta and the datum in the data domain. Usually, this is achieved by pre-processing the data to ensure the feature vector of each datum lies inside a ball of some radius. Or we can directly clip the L2 norm of individual gradient by a threshold. The ADMM algorithm was proposed decades ago and has recently been widely used to solve optimization problems in machine learning. Consider the optimization problem of summation of two functions. It forms the augmented Lagrangian of the problem and solves the optimization problem by alternating the iterations below through a dual variable y and a penalty parameter zo. Therefore, x and z are updated in an alternating fashion, and the minimization over x and z are separated into two steps. This can make an otherwise hard-to-solve optimization problem solvable in a sequential manner. Now let's move to the algorithm part. Our proposed private algorithm is based on one variant of ADMM called stochastic ADMM. This variant was proposed based on the observation that for ADMM problems, usually only one of the two added functions is data dependent, and it is both expensive and unnecessary to exactly solve its minimization step for each iteration. To be specific, let f be data dependent and h be data independent. Then ssADMM replace the augmented Lagrangian by an approximated augmented Lagrangian L hat of zo defined at iteration k as formula 12, where b is the portion of the data accessed at iteration k. For this modified Lagrangian, one can derive an exact solution for each x minimization step instead of solving an expensive ERM problem. For L1 regularized ERM, let h of z be the regularization term, then the constraint reduces to x equal to z. Then by taking derivative of L hat of zo, one gets equation 13 as the x update step. Note that this is the only data-dependent step in our algorithm. Therefore, we apply the Gaussian mechanism to satisfy privacy. The other steps are all data independent, such as the update of the dual variable y and the private variable z. For the regularization term h of z, since we use L1 regularization as an example, we can use soft thresholding technique to acquire the exact solution to minimize it, where the soft thresholding is defined here. We proved that our algorithm satisfies Renyi differential privacy for any given integer value alpha. This is through the Gaussian mechanism, the RDP version of privacy amplification by subsampling lemma, and the RDP composition lemma. We also proved that when the learning rate is chosen appropriately, this private algorithm has a decent convergence rate. Both proofs can be found in our paper. In addition to gradient perturbation algorithm, we also proposed a model perturbation algorithm. Different from perturbing the gradients, this algorithm uses the unperturbed gradients to do the model calculation for a whole step and keep track of the L2 sensitivity of all data-independent model vectors. To calculate the sensitivity, we look deep into the property of the soft thresholding and the dual variable update, and conclude the upper bounds of sensitivity for all three model vectors. The detail of the calculation can be found in the paper. This algorithm can be considered as a multiple-time output perturbation algorithm. Empirically, we found that it performs well in attribute selection tasks for regularized optimizations. We also proved that it correctly satisfies RDP. To summarize our algorithms, by utilizing ADMM, we are able to separate the unregularized gradient descent part and the L1 regularization part into two steps, so that the pure gradients can be computed and perturbed in X minimization step. For other algorithms which did not separate the data dependent step and the regularization step, only the proximal gradient has to be used to handle the L1 regularization due to its nature of non-differentiability. Next, let's move to the experimental result part. We perform our experiments on L1 regularized logistic regression and hybridized SVM. Both models are binary classification models, and the objective function of these two models are shown here. For hybridized SVM, we set the hyperparameter h as 0.5 for all experiments. We compare our proposed algorithm with a series of baseline models. Note that although a lot of differentially private ERM techniques exist, many of them cannot be applied to L1 regularized classification due to that they require the object function to be smooth. So we compared ours with the ones which can be applied on non-smooth regularizations. DPSGD is a naive gradient perturbation algorithm which perturbs the proximal gradients with the Gaussian noise in the L1 regularization case. mpADMM is a distributed learning version of ADMM, where each party transfers the perturbed primal variables to the center, and the center draws a consensus of the parties, then transfers the primal and dual variables back to each party. ADMM object perturbation is an ADMM version of the object perturbation algorithm. At each iteration, the trainer optimizes a perturbed non-regulated objective function. Therefore, in practice, it is differentially private only if the objective function is exactly solved. We applied our experiments on two real datasets, adult and IPU-MSBR, and one synthetic dataset. The two real datasets are census datasets about information of humans. For the synthetic datasets, we create a sparse dataset to test for the attribute selection. To be specific, we created a 100-dimensional dataset where only 20 attributes are used to determine the binary label of each individual. We use a criterion psi-k to measure the coverage of relevant attributes if top k attributes suggested by the attribute ranker were selected, as an evaluation of attribute selection performance. Since our algorithm satisfies RDP, while others satisfy DP, we use the RDP to DP conversion proposition to convert our results to epsilon delta DP. We fix delta to be 10 to the negative 8 for all results. Figure 1 illustrates the testing data accuracy on top and object values on bottom of the algorithm's trading off with privacy parameter epsilon in regularized logistic regression. And figure 2 shows the results for hybridized SVM. We can see that both binary classification models, ssADMM outperforms other algorithms in most cases. Comparing ssADMM with DPSGD, the advantage of ssADMM is more obvious in the objective value. This is in accordance with the fact that stochastic ADMM outperforms proximal gradient in non-private settings, and it is more robust to noisy data with outliers. Figure 3 shows the classification performance of each algorithm on the synthetic data, and Figure 4 shows the performance of attribute selection. Although classification accuracies are close for our models and DPSGD, we can see that mpADMM can detect more relevant attributes, especially in the low epsilon range. ADMM object perturbation, which is an algorithm proposed for feature selection, can outperform ssADMM and DPSGD in low epsilon, but it requires more epochs in training compared to other algorithms. Therefore, if we know the data is sparse and want to do feature selection, mpADMM is preferable. To conclude our paper, we present two privatizations of stochastic ADMM under Renyi Differential Privacy. Both algorithms can be used to solve optimization problems with complex structural regularizations that induce sparsity. This concludes our paper, and thank you, and I hope you enjoy the rest of the day.